All right, welcome to Materials Science. We are talking about phase diagrams and microstructures that form and phases. And so what we are looking at right now is the iron Fe3C phase diagram. So this over here on the right hand side is what we call a line compound because it exists at exactly 25 weight percent carbon, which corresponds in weight percent to be 6.7 weight percent carbon. So we're looking at the iron Fe3C phase diagram. I want to point out some reactions. So this is review. Up here we see an invariant reaction at 1493. That particular reaction is called a pearlite reaction because we have two different phases, delta and liquid, turning into another solid phase, which is called gamma, which we call austenite. Gamma is austenite, and by the way, that's face-centered cubic. The second invariant reaction we have occurs right there at 1147 degrees C. Here we have liquid turning into the phase that it finds over on the left-hand side, which is gamma, and the phase that we find over on that side, which is Fe3C. So this reaction is a liquid, turns into gamma plus Fe3C, and that is a eutectic, right? A eutectic reaction. The last reaction, the invariant reaction we see, is at this temperature of 727. This reaction tells us that gamma turns into these two phases. The phase over here on the left, which is called alpha, ferrite, which is body-centered cubic, and the phase we find all the way over there, which is that Fe3C again. And so we see that gamma turns into alpha and Fe3C, and that is actually called it's like eutectic, and so because it's like eutectic, we call it eutectoid. What makes it an oid is that we have a solid phase turning into two other solid phases. This is a very important reaction, and I want to point out a couple things about it. It only occurs to gamma that has exactly this composition, which is 0.76 weight percent carbon. So gamma with that composition, so that's the number right here, 0.76. When we take gamma and we cool it below 727, it can't exist anymore, and it has to turn into alpha and Fe3C, and that involves a lot of diffusion. And so when this happens, when gamma at this composition of 0.76 turns into alpha plus Fe3C, it forms a very special microstructure called pearlite. Pearlite. And that looks like fine grains of alpha, fine grains of Fe3C, fine grains of alpha, fine grains of Fe3C, fine grains of alpha. And then some more might be going this way, and so you end up seeing microstructures that look like they have a bunch of parallel lines in them. And so whenever you see microstructures that kind of resemble that, you know that it had this rapid formation and rapid diffusion that has to happen, right? Because gamma, which has this composition of 0.76, carbon has to get out of it in order to form the ferrite, and iron has to get into it, right, in order to form Fe3C. So there's a whole bunch of diffusion going around, and because of all that diffusion, you end up with a very fine microstructure. Okay, so that was all background, and now I'm going to kind of erase all this and work on solving the problem. That's stuff I need you to kind of know going into this problem, in other words. Okay, so this problem is asking for us to solve three different things. And we'll start problem number one with the color red. So I'm going to try to mostly use red for this, and then I'll move to another color. So let's move to red right now. Okay. So what phases are present? And we're going to answer that first at 20 degrees C. And remember, this is our alloy. Okay. As soon as you know the alloy composition, in other words, the composition of the alloy is 2 weight% carbon. So as soon as we know that, what we do is we draw a vertical line going all the way on up through 2 weight% carbon in order to answer that question. And so we notice on this left-hand side, it doesn't even go to 20 degrees C, so we'll answer it at 400. That's the best we can do. We're going to choose this temperature here to answer that question. So what phases are present? Well, look, we're in a two-phase field. There's alpha and there's Fe3C. So the answer to number one is we have alpha and we have Fe3C. Alpha, remember, that's ferrite, remember the names, and this is cementite. It would be correct to say alpha. You don't necessarily need to know the word, but notice the word is actually on the phase diagram. So we answered what phases are present. Now, I'd like to answer this part. What are the compositions of the phases? So to find the composition of the alpha, what we do is we from our composition of 2, right, we're going to read left, left, left until we hit a line. And you can see this line is pretty much at almost pure iron or 0 weight% carbon. And so we can say the composition of alpha, I'm going to say approximately 0 weight% carbon. It's not exactly 0. It's probably 0.01 or something like that. 0.001, I don't know. But it's a very low number. And now, what's the composition of Fe3C? That's going to be exactly read left, read right, right, right until you hit a line. And I just want to point out, cementite is a line compound. It only exists at exactly 25 atomic percent carbon. So its width is invisible to us. But anyway, so this is why I'm telling you the composition of Fe3C is 6.7 weight% carbon, or you could have said 25 atomic percent carbon. Both of them are correct. And we can read the atomic percent up here. So we've answered that and that. Now I want to focus on how much of each phase is present. All right. So to do the how much, what we do is we use the lever rule. Okay, and so for the lever rule, the tie line of interest, I'm going to do a little bit of cleanup again. The tie line of interest that we want to pay attention to is the intersection of the overall alloy composition with, and I'm drawing it there so we can visibly see it with that, okay? So, sorry, I meant that to be a flat line. So we use the lever rule. This is one point of interest, that's another point of interest, and that's another point of interest. So the fraction of it that is alpha, because we have two things present, alpha and Fe3C. The fraction of it that's alpha, and now I'm going to go to, I guess black. It will equal this line segment length divided by this line segment length. So I'm gonna kind of put that here, divided by that, and I'm gonna put exact numbers in it. And in other words, it will be 6.7, which is that point, minus 2 divided by the whole line segment length, which is 6.7 minus about 0. So that is 4.7 over 6.7, and when you do that calculation, the fraction of that is alpha ends up being 0.21. This means that 21% of it is alpha, which of course we call ferrite. It's body center cubic ferrite. What's the rest of it? Sorry, this is not correct. That should be 0.79. I have garbled myself up here. To erase this right away, this calculation gets us to 0.79, i.e. 79% is alpha, and therefore the fraction that is Fe3C is equal to 1 minus 0.79, or 21% Fe3C, or cementite. Okay, so that gets us through part 1 of the problem. And I'm going to move now to discuss part 2 of the problem. And part 2 of the problem also involves sketching the microstructure. So to do that, I'm going to erase again so I can write directly on the diagram and not flip back and forth. Okay, so we are now answering part 2. Okay, let's go to green for part 2. So in part 2, we are asked what microconstituents are present. And then there's going to be the how much, and then we're going to know what is the composition of each microconstituent at 20 degrees C. So what is a microconstituent? You'll see as we solve this problem. So to answer this one, again, it is very helpful to draw a line through your overall alloy composition of 2%. And let's just start ourselves off from way up high. At way up high, we're liquid. As we cool down, notice we enter a solidification zone or temperature range where austenite begins to form. And then at this point right there, notice we're in a region where all of it is austenite. Okay, so right there at this temperature, I want you to imagine what the microstructure would look like. So as we entered this from the liquid, as we entered the gamma, the region where gamma was solidifying, we began to form some gamma. Then that gamma grew bigger, it grew really big, and now it's 100% gamma. And so what we basically have are large grains of gamma at that temperature, which is what 1100s, let's say at 1120 about. At 1120 degrees C, that's what our microstructure looks like. It's all gamma. It's large grains of gamma because it had a temperature range over which those large grains could form. This is an important thing for us to know because it helps us answer what happens next. All right? So what happens next as we continue to cool is that we begin to nucleate Fe3C out of the gamma. So let's imagine that Fe3C has this orange color. I'm going to associate that with the Fe3C color. And so what I'm saying is that some gamma begins to nucleate. Where? Well, it likes to nucleate at imperfect parts of the crystal. So it nucleates at the grain boundaries, which are certainly imperfect because it's a region where two crystals grow together, And then, right, we're going to continue to cool, we're going to continue to cool, we're going to continue to cool, we're going to continue to cool. And as we do that, the amount of Fe3C grows. And so, you grow more and more and more of it. It grows, and then thickness of this stuff along the grain boundary gets a little thicker. And so finally you end up with Fe3C completely lining, if you will, the grain boundaries of this material. Now, what fraction of it is Fe3C? This is going to be important for us to answer because it'll also help us understand what fraction of it is gamma. So, and we have to answer this in order to proceed with the rest of the problem. So let me draw a tie line. At this point, I'm going to switch to blue. So at 728 degrees C, so I'm calling that temperature 728 degrees C. Why 728? Because it's just 1 degree above this. At that temperature, we've got, you can see that the tie line will intersect there, and of course at our overall alloy composition. And so the fraction of the material that is Fe3C, which is of course nucleating out of the gamma, will equal this line segment length divided by the total line segment length. In other words, the fraction that is Fe3C will equal, and let me just draw this down here so I have a little more room, 2, that's that point right there, 2 minus 0.76 divided by 6.7 minus 0.76, which is that point right there. And why did I choose 0.76? Because that's where the tie line hit at 728. All right, so 2 minus 0.76 divided by 6.7 minus 0.76 is equal to 0.21. So that is the fraction of the material that is Fe3C at 728. And therefore, we've got 0.79 of it, or 79%, that is the fraction that is still gamma at 728. Now this is super important. And so I want to clean up again a little bit because you will see why. Okay. So now I want us to imagine that we are, and what color can I be now? I don't know. Let's go back to black. So now I want us to think about going cool through 727 to 726 degrees C. That's what we want to do next. So I'm going to draw a tie line at 726. Okay. So that tie line, of course, we've still got our overall alloy composition of 2. So that's an important point to us. That's an important point to us, and that's an important point to us. We know that we are in a two-phase field. So we're gonna have alpha, and we're gonna have Fe3C. And now we end up in this kind of important question of microconstituents. All right, and so follow me carefully here. So that Fe3C that we already formed stays there. So the Fe3C, the Fe3C that already formed has a name. So we call this proeuctectoid Fe3C. And so we've got 21% of this stuff remains that stuff, okay? So that's one thing that we've got. And this just means above, stuff that formed above the eutectic temperature. Okay, so we got that. Now, the second thing we've got is what happened to this, okay? So that other 79% of stuff, or 0.79 as a fraction, it was gamma that had this composition of 0.76. And we already talked about what happens to material with that composition. Material of that composition turns into pearlite. So we've got pearlite. We've got 79% pearlite. What is pearlite? It's just a fine mixture of alpha and Fe3C. It's a microstructure. So we have proeutectic Fe3C and we have pearlite. So those are the microconstituents that we have present. And that's how much of them we have. And you see now, I think, why we had to spend so much time thinking about what was going on at 728, because it gave us the answer to what's happening below 727. And by the way, this will be the same answer all the way down to room temperature. So by the time we answer it at 726, we've also answered it at room temperature. All right, and so the composition of each microconstituent, that's kind of a strangely phrased question. So the composition of Fe3C is still 6.7 weight% carbon. And the composition of pearlite, right? Oh, the overall composition of pearlite, I guess you could say it's 0.76 weight% carbon. But remember, it's a mixture of alpha, which has 0 or almost 0% carbon, and Fe3C, which has 6.7 weight% carbon. All right, and the very last thing we need to do is to sketch the microstructure, and this is where it kind of all makes good sense to me. So to do this, I'm gonna kind of redraw this down here because it will help us see what happens, right? So if you remember, we started off with 3 large grains of austenite, and then we nucleated about 21% of it, exactly about 21% of it turned into Fe3C, which was the proeuctectoid Fe3C. And I've drawn about 21% of the area occupied by orange, and I'm eyeballing this, I'm not being very scientific here, that looks like about 20% of the area. And now, right above 727, this stuff was gamma. But as we cool down below 727, the gamma turns into pearlite, right? It turns into this microstructure called pearlite, which is alpha and Fe3C, the fine grain microstructure. And so we can draw that. I'm going to draw that by writing little tiny plates of, I don't know, I guess I'm drawing alpha, and then we'll make the white stuff be the cementite. So I'm trying to draw, pearlite. You can see I'm not a very good artist here, but the point is this stuff is a mixture of alpha and Fe3C. One of them is white and one of them is black. And so, you would continue to fill up, your space. On an exam, you're going to be doing something like this, like kind of quickly cross-hatching it. And so we call that pearlite, right? Okay, so we have sketched the final microstructure, and as I said, don't worry about the fact that this phase diagram ends at 400. If it's equilibrium cooled, we're going to end up with this overall microstructure. And now just a few comments about the microstructure. So if we put this part into service and we begin to load it up. Remember, a dislocation that's trying to move through the pearlite has a very difficult time moving through the pearlite, right? It has to, it slows it down immensely for a dislocation to try to work its way through pearlite. And cementite is a pretty brittle material, but it's also hard. So the properties of this particular microstructure would be that it would be a brittle but pretty darn hard material to steel. And so that concludes this extensive discussion of this particular learning exercise, and I thank you for your attention.